For this lesson, we'll be going over bipolar junction transistors, also known as BJTs. BJTs are a three-terminal device whose output current, voltage, and/or power are controlled by its input. These three terminals are known as the emitter, the base, and the collector, and the BJT is a current control device. To give you some imagination of how it operates, this is a very crude manner. Look at the illustration below. You'll see a person adjusting a dimmer switch. Well, the person controlling it, you can consider the base. They're controlling the flow of current through the collector and the emitter going to the light in your room. So that'd be a very crude manner of how to imagine how a BJT works. Just to review some of the basics, there are two BJT types, NPN and PNP. This is where you have two N types with a P type in the center where the base is at, and the PNP is where you have two P types where the N type is where the base region is at. Now, as far as you want to remember which one's which, think of the arrow direction in the illustration. If the arrow is pointing outward, it is not pointing in. Example, not pointing in is NPN. And if the arrow is pointing inward, then it's pointing in PNP. So that'd be an easy way to remember the acronyms as far as which BJT is which. Now, BJT has three operating regions: saturation, cutoff, and linear, also known as active region. Saturation is when the collector current reaches its maximum value. Think of it as the BJT is shorted out. Next is the cutoff region. It's where the collector current is nearly zero, or think of the transistor having opens everywhere. And then the last region, which is the one we're going to do examples of, is the linear or active region. And this is anywhere in between saturation and cutoff. And we have illustrations below to see how it would look if you had a equivalent circuit. To elaborate more on saturation and cutoff regions, we do have an illustration below in our graph where it shows the cutoff and saturation region. Now, in between those two regions, the red and the green, that is your active region. Your saturation region, like we talked about, is simply a short. Is where your BJT is at its maximum value no matter what you do. And your cutoff region is if your junctions are in the reverse bias and there's no current flow or it's nearly zero on your terminals. I want you to think of it this way. Saturation, if you're opening a dam, saturation is where the dam doors are completely open and it can't open any further. You have the maximum amount of river flow or current flow going through that transistor. And the cutoff region is when your dam doors are closed. No current flow is being flown through it whatsoever. It's nearly zero. So try to think of it that way as far as how to imagine how a transistor works in those two regions. Okay, now we're getting to the meat and potatoes of the lesson, the DC analysis of BJT. Now for this lesson, we're only focused on the DC analysis because you have to learn how to do that before you go to the AC analysis or the small signal model. So we're going to go through the steps of how to perform the DC analysis. Step one, we're going to remove the AC elements out of our circuit. This includes removing your capacitors and removing your AC source. The reason you remove your capacitors, because capacitors act as opens when performing the DC analysis. So if you actually calculate this in your impedance calculations, 1 over 2 pi FC, well, in a DC analysis, there is no frequency. So if your frequency would be 0. So if it's 0, you have an impedance that's almost infinite, so it acts as an open. So if you look at the illustration below, we have a full circuit with a DC source as well as an AC source. So we're eliminating the AC analysis out of this circuit just so we can understand how the DC analysis works, because you need to know how to do DC before how you do AC. Next, we're going to try to simplify the DC circuit using Thevenin theorem or any other theorem you'd prefer. I usually choose Thevenin just because it's easier on me. And again, we're going to try to either simplify it if we can. For example, the illustration you see below is a voltage divider bias of a BJT. So it has two resistors in a sense in parallel with that base current or that base terminal. So we want to simplify the circuit. That way we have a single base resistance with a single voltage at the base. If we're able to do that, then we can start plugging and chugging in our equations to the right. The last step is to take our simplified circuit and transform it to the linear model. In the illustration below, I had our circuit from the previous slide, and I transformed it to the linear model that's provided from the FE handbook. And this same model is usually provided in a majority of your textbooks or your PE references. Now, something I want you to be aware of, the voltage between the base and the emitter does change. It is considered constant, but it does change based on the BJT. If it's a silicon, it's kind of like the diodes. It's 0.7 volts. It's germanium, 0.3 volts. Just be aware that those are constants, but you have to choose between the two depending on which transistor you have. The very common one is 0.7 volts. So majority of calculations, it's very, I'd say the odds are good that it's going to be a 0.7 volt drop. Also, I did provide a few equations to the right, the ones we're going to use in some of our examples. So once we have our linear model, we might be able to start plugging and chugging using these equations to find whatever answer they're looking for. And the last thing of note, be aware that I use all capital letters for all my subscripts when determining these equations, or when I'm displaying what I have on my circuits. For example, my collector current, it's a capital C for IC, and then same thing with the current for the base, current for the emitter. They're all capital letters for the subscripts. This is very important. When you do an AC analysis, they're going to be lowercase. And when you do the AC analysis, they may ask for uppercase depending on what equation you're plugging and chugging in. So be aware there are two different subscripts based on what they're asking for. Lowercase is AC, uppercase is DC. And we're only doing the DC analysis for this lesson, so be aware all of my subscripts should be capital letters. All right, for our first example, we're going to jump right in with a few fundamentals about BJTs, as well as we're going to solve one of the easier of the BJT circuits. All right, so it's going to go over a few things. One, if you look at the equations, I did supply with a hefty amount of equations here. Some of them are current, collectors, base, emitters, and as well as the betas. And then I also included voltage equations. Now there's a few things you need to be aware of. Current flows in this direction when you're doing with NPNs, not pointing in. See how the arrow is going outward? So this particular one is an NPN. Okay, and current is flowing downward from VCC power supply through the collector resistor all the way down to ground down here. One current direction flow. The other direction is coming from your base down through your emitter. So you have two different current flows going to the emitter. Hence why you come up with the equation to your right down here, where you have the emitter current equals the base current plus the collector current. So I just want you to be aware of that, so that when you're trying to calculate your emitter current, you have to include your base as well as your collector. It's not isolated. It does control how the current flows in this equation. The base does control this. However, you have to add it in. It may control it, but it still is going to be implemented into the emitter current. I want you to be aware there's two equations I supplied here, base current and emitter current. Now these are hefty size equations that I have here that we're going to use later on in the next example and a little bit of this one. This was not in most of my books. This is something I had to derive just by searching greatly through all my references. I'm supplying this for you because I noticed I was able to take these two equations and find a lot of information just off these two. A majority of books and your FEA handbook supplies usually these earlier ones. They're very simple, but it doesn't give you the full picture as well as doesn't minimize your speed. Our goal is here to get you through these problems quickly and accurate as possible. All right. So now that we talked a little bit about this, let's go through our steps. Step one, we're going to remove our AC components. All right, as we talked about earlier, capacitors act as DC blocks. Because if you do an impedance check, 1 over 2 pi FC equals infinite resistance. Because DC does not have an AM signal, which means there's no frequency, giving that a 0. And it hence giving us an infinite resistance. So this would be considered an open, and this would be considered open. So let's remove those out of the equation as far as step one and get rid of our AC elements. All right, next, or step three, we're going to take our equivalent circuit here. This is already simplified down, and we're going to transfer it to our active region circuit. That way you get a little visual of what's going on here as well as how to solve these equations. So I'm going to go ahead and transfer this to it. So it's going to look something like this. Let's see if I can draw it halfway decent. Now, just to make this easier for me, I kind of cheated and just went ahead and copy and pasted this from my slideshow. So just to go ahead and fill in our active region here, we have 12 volts. And this is coming from VCC, but since it shares the same voltage here, this is going to be also VBB. Okay. Next is our base resistance, which is 400K. This is our VBE also known as where our voltage drop like diodes go. This we're going to assume is silicon, so it's going to be 0.07 volts, and this is our base emitter voltage if you're curious. So that's that guy. Okay, next RC is going to be 2 kilo, and then RE, or resistance at our emitter, is 0, just because there's nothing there. And then we go back to 12 volts, VCC. So right there, we just converted this circuit to our active region circuit. Nothing special yet. This is all just putting it in there. That way you visually see how I'm doing this. We're just going from one step to the next. Okay, now we're going to start doing a little bit of plug and chug method. Now, we're going to go back to this big equation right here, because this is a very good equation that was derived from several references. And not all of your books, and like your FE handbook, doesn't refer to this equation, but we're going to use it. So let's go ahead and plug and chug this. Let's find our base current. So it's IB equals VBB, which is 12 volts. This is your base voltage right here. And this will change. It won't always be VCC. It won't always be this guy up here. But since we don't have any other resistors or anything else manipulating this base voltage, for the sake of argument, it's going to be 12 volts. Okay. Then, since it's a silicon transistor, it's minus 0.7 volts. This is over. Now we have our base resistance, which is 400 kilo. Please excuse the handwriting. Plus, and this one's going to be 210 for beta, and that's plus 1. Put in parentheses just to keep it the same. And then times RE. Well, here's where the great part comes in. There is no resistor right there. So you have 0 ohms, 0 resistance. So this guy is actually going to be 0, which means 0 times 210 plus 1 is 0. I'm going to give a base current of 12 volts minus 0.7 volts over 400 kiloohms. And if we plug and chug that in our calculator, it's going to give us an answer of 2.825 times 10 to the negative 5 amps, also known as 0.028 milliamps. Put this up here real quick. So our base current is, we'll say 2.825 times 10 to the negative 5. That's amps. All right. Now I'm going to make room down here to find our collector current. So let's get rid of this. With our base current, we can just about find anything, because once you have that, you can plug and chug a few of these just right in. For example, so we have our collector current right here. So if you have the base current times beta, you have our collector current. Not very difficult at all. So IC, I'll try to make my handwriting look halfway decent, times beta, multiply times our base current. And this is going to give us, let's put some values in there. So 210. This is usually given. So that's why I went ahead and gave it for this equation. And 2.825 times 10 to the negative 5 amps. Okay, plug and chug that in our calculator. I'm going to go say collector current of 5.9325 milliamps. And that was pretty easy. That was a simple plug and chug. Once you found the hard one, the rest of it was pretty easy. So we're going to put this guy up here real quick. 5.9325 milliamps. Now I know I'm going a little excessive on how many decimal places I'm putting in, but I'm just doing it just because that way you see where I'm getting all these numbers from, because I'm just keeping them in my calculator. All right, next, find VCE. VCE is this guy right here. That's our voltage between our collector and our emitter. So we're looking for that guy. So I'm going to clean this up and we're going to see if we can find that one. Now VCE we can find two ways. We can use it finding this equation or this equation, and just based on how you manipulate it if you want to use the bottom one. But since we already have it right here, let's use that guy. So we have VCE, voltage at our collector and emitter, and this is right at the transistor, equals VCC, actually I'll just write it out, minus collector current times our emitter resistance plus our collector resistance. I don't know why my pen decided to start smearing today. So we know this is 12 volts because that guy right there. So 12 volts. And usually when you see VCC, it's referring to this guy right here. It may not always be labeled as such, but I notice it's very common, so I'm going to stick with the common nomenclature here. Minus, we know IC now is 5.9325 milliamps times, now here's the good news, we don't have any resistance at the emitter. There is no resistor there, so it's 0 plus RC. So we need the resistance at the collector, which is 2K. So does that make sense how we got that? So if you look at how we got it here, current is flowing this direction with no resistance right there, so it's that guy right there. All right, so plug and chug that in our calculator. Pretty simple. It's going to give us an answer of, so it's going to be 12 volts minus 11.865, and that's going to give us an answer of 0.135 volts. So between these 2 points right here, it's going to have an answer of, right there, 0.135 volts. And this was a pretty easy one to solve. However, it's just going through it and as far as understanding how we're getting these. Now again, think about this guy right here as a diode, hence why you have a 0.7 volt drop, and that's why you got to use it in your equations here. And these two equations right here are going to be your bread and butter as far as finding some of your answers. It may not be in some of your textbooks, but I'm providing it to you so that way you can move along forward and quickly. Let's do one more example so we can get a little more experience with BJTs. All right. For our next example here, we have a voltage divider bias circuit. There's two resistors at the base, which means we're going to have to do a little bit more circuit analysis before moving into plug and chugging mode. All right. So we're going to start off just like we talked about earlier. We're going to do step one. We're going to move the AC components. So we're going to move all of our capacitors, our AC source, from this circuit. So right there, by the way, I just want to put this on record. So that node right there is where our load resistor is. So any current that's flowing this direction is for our load resistance. So right there, just give you a heads up, that's where our load is at. I'll just put L for now. So let's go ahead and isolate the AC components from the circuit. Okay. Step two, we need to simplify the circuit. Now I'm not going to mess with the collector or the emitter right now, but I am going to mess with the base since it has two resistors in parallel with it. For the base, we need to find the equivalent base resistance as well as the voltage, because it's not going to be 12 volts right at this point. It's not like the last circuit. So we need to find the base voltage, VBB, and we need to find the base resistance, or in this case, base Thevenin. Now, if you're curious how I'm getting this, or how I'm getting the actual values here, current is flowing through this direction, and then we have a voltage drop on this resistor right here. So that means there's going to be voltage right there, and then another voltage drop, because current is flowing this direction. So, which means our base current is going this direction. That's our IB. However, we got to find what that is. And I told you in the slide that we're going to use either. So we can use Thevenin theorem or any other circuit analysis you would like to use. To let you know how to do a Thevenin theorem for this particular circuit, it's not very difficult. Let's look at it from a different point of view. Right now, you have a voltage source, 12 volts. It's going to one resistor. That one resistor is going to the base, we'll say right there. Then we have a piece of that base going straight to ground. That's where ground is. See how I did that? That's the 5K ohm resistor, and this is the 10K. So if you had to rewrite this, this is exactly how it looked. This is one point right here. Let's say it's A, and that's B. A and B. So if I rewrote it, that's how it looked just from looking at it from this angle right here. Okay? Doing the Thevenin theorem, how do you find Thevenin resistance? Well, you short your voltage sources, open your current sources. If I short this, it's going to leave your 5K and your 10K in parallel. your Thevenin base resistance right there. Very simple. So it's going to be 10K in parallel with 5K. And that would give us an answer of 3.33 repeating kiloohms. So that right there, that's our Thevenin for our base. Next, we need to find the voltage at this point. Same thing, we can keep the same model right here, but now we need to do the voltage divider rule to find what the voltage between points A and B are. Using our voltage divider rule, very simple. We'll say VBB equals 5K over, that's 10K plus 5K. It's going to be multiplied times VCC, so it's going to be 12 volts. It's the Thevenin equivalent at our base of 4 volts. See how I did that? All I did was try to find the voltage right here in our little Thevenin equivalent circuit there, and it's going to be 4 volts. Because if you're doing a series circuit here, this would eat up 8 volts, this would eat up 4 volts. So we have VBB, and we have our base resistance. So, I'll tell you what, I'm going to put this to the side and clean it up. So I cheated a little bit. I went ahead and, again, copied the schematic off my slides just to make it easy on me. Alright, so we did the Thevenin equivalent for the base side, which means that is 3.33 repeating kilos. And for the voltage at the base, it's going to be 4 volts. Okay, RC doesn't change, 2 kilo. Emitter doesn't change, 1 kilo. And VCC does not change, 12 volts. So all I did here was just clean up this side of the circuit, the base side. That's all I did, just the base of the transistor. So we did step 2, we simplified the circuit. Now we need to take this guy and go to the active region circuit. So I'm going to try to move this over and I'm going to paste that guy in there and we're going to fill that in. Alright, just to try to make room, I went ahead and moved a few things around. I know it looks a little skittish, but this is I didn't want to delete everything off the page, that way you can see what I'm doing. Alright, so I'm going to fill all these in. So VBB, that's 4 volts. And this is the base resistance, which we talked about is 3.33K. We're going to assume that's 0.7 volts as usual. Until further notice, always consider 0.7 volts unless they tell you different. Alright, our VCC is 12 volts. Collector resistance, 2 kilo. Alright. Emitter resistance is going to be 1 kilo. Alright, so we went ahead and filled in our active region circuit. Step 3 complete. Now let's see if we can plug and chug a few of these. Alright, now we want to find our base current. Well, same thing as last time, I want to use this bad boy right here. So same thing as last time. So it's IB equals, now VBB instead of 12 volts, it's now 4 volts. 4 volts minus, and this is going to be 0.7. We're always going to assume it. We have our base resistance, which is 3.33 kilo, plus beta, which is 153, plus 1, and that's multiplied by 1 kilo ohm, because that's our emitter resistance. Alright, we're going to plug and chug this in the calculator and see what we get. 2.097, I'll just go ahead and do 5, why not, times 10 to negative 5 amps. And we can translate this to 0.021 milliamps. Just keep it clean. So right then there, I'll put that up there. 0.021 milliamps. Okay. Now, let's see if we can find our collector current. I'm going to erase this down here. Beta and the current. Now we can find the collector current, which is that guy right there. So it's going to be IC equals, it's going to be 153 multiplied times 0.021 milliamps. That's a very simple plug and chug one. Put that in our calculator. This is 3.213 milliamps. Okay, so now we have our collector current, 3.213 milliamps. I'll do my best to see if I can sharpen my pencil on this one because it's not exactly sharp as I want it. All right, we'll erase it again. Next, fire emitter current. So we're going to use this guy right here. Same thing. We can plug and chug it this long ways, or we can add these two guys together. So I can either use one of these two guys right here. Well, I'm going to be lazy and we're going to save time. We're going to add the collector and the base current together. And I'm doing this for two reasons. One, it is quicker. And two, just to show you that current does flow the same direction. It does go like that. So you have 3.213 milliamps plus 0.021 milliamps. Now for those of you who have access to multi-sim or any of your simulators, you can put this equation in there or put this circuit in there and you'll get the exact same answers. It's going to give us an emitter current of 3.234 milliamps. That one was relatively easy. And again, if I wanted to, I could have plugged and chugged it in our big one right here and you would have the same answer no matter what. But for sake of time, we're going to save time by using that guy because you only got 6 minutes on the test, so you got to make it count. Last one. This one's a little trickier. Find the voltage at the load. Now I talked about earlier, when you have a load resistor right here, you want to actually find that voltage right there. So I want to clean this up real quick. You have VC, you have VCE, and then you have VE. When you add all those together, you should have VCC. Hence why you have this guy right here. That's VC, VE, and then VCE. That's not there for a coincidence. That is there on purpose. So if we want to actually find the voltage right there, if we took a meter between there and ground, what are we going to get? Well, VE plus VCE is going to get what we want for our load. Well, voltage at our emitter is pretty easy because we have our current, we have our resistance, so then we know our voltage right there. What we don't have is VCE, but we have all these other guys. Well, we can manipulate this pretty easy, or we could say VC from 12 volts should give you the remaining values right here. So in other words, VCC minus VC gives us our load voltage. Because once the voltage drop across that 2K ohm resistor happens, all it's left is this guy right here. So VC is same thing, our resistance times our current. So plug and chug that in our calculator is going to give us a voltage drop of, it's 12 volts minus, and we'll say it's 3.213 milliamps times 2 kilo ohms. Plug and chug that in our calculator is going to give an answer of 5.574 volts. So all I did was find our voltage drop right there, which is 6.426 volts. And then the remaining voltage between here and here is 5.574 volts. That's all I did. If we want to find our load voltage, it's 5.574 volts. It's very rare when I ask for that in that way, but I want to go over it that way you're aware of how I came up with these. So remember, there's always voltage drop right there, your collector resistance and your emitter resistance. On our next lesson, we'll most likely go over our small scale model and our AC analysis of BJTs, and we're going to talk a little bit more of the DC analysis going into the AC analysis. Hopefully I gave you enough information here to confuse you and make you dangerous, and I hope you all have a good evening.